Through the rust-colored haze of Mars, descending at 12,000 miles per hour, a silver tower falls towards an alien world. Inside, human hearts beat against the crushing deceleration. Outside, friction transforms atmosphere into plasma, wrapping the hull in a cocoon of fire. There is no sound here, only the deep vibration of metal under impossible stress. This is the moment everything depends on. The heat shield holding, the guidance systems responding, the engines, cold and dormant for 6 months, reigniting precisely when commanded. One failure, one miscalculation, and the dream of becoming a multiplanetary species ends not with a whimper, but with a crater on a world that has never known footprints. Elon Musk has painted a vision so compelling it feels almost inevitable. Starship, the largest rocket ever built, ferrying humans to Mars within this decade. Cities rising from Martian soil. Humanity spreading beyond Earth, securing our future among the stars. It is a dream that stirs something ancient within us, the explorer's impulse, the pioneering spirit that has always pushed our species beyond the next horizon. And yet, beneath the soaring rhetoric and the stunning test flights, there exists an uncomfortable question that few seem willing to ask aloud. What if the physics simply don't allow it? What if the gap between engineering ambition and biological reality is wider than we've been told? This is not about cynicism. It is not about doubting vision or dampening hope. The engineers at SpaceX are among the most talented minds working today, pushing boundaries that seemed immovable just years ago. But science does not negotiate. Physics offers no compromises. And Mars, for all its proximity and familiarity, remains profoundly hostile to human life in ways that clever engineering may not fully overcome, at least not yet, and perhaps not safely. Tonight, we will journey through the genuine challenges that stand between Starship and a successful crewed Mars landing. Not the challenges of funding or public interest, but the hard realities written into atmospheric density, radiation exposure, human physiology, and the unforgiving arithmetic of planetary entry. We will explore the heat shield problem, the descent through an atmosphere too thin to slow you gently, but thick enough to tear you apart. The belly flop maneuver, elegant in concept but gambling everything on untested precision. The engine Relight challenge, trusting machinery that has been exposed to deep space cold and cosmic radiation for half a year. The biological toll of months in zero gravity, arriving at a world where you must immediately perform complex tasks with weakened muscles and brittle bones. This is not a video designed to crush dreams. It is designed to illuminate the distance between what we hope for and what we must solve. Some of the brightest minds on Earth believe these problems are solvable. Others quietly wonder if we are moving too fast, risking lives in pursuit of timelines driven more by ambition than by readiness. The truth, as always, likely rests somewhere in between. In the patient accumulation of knowledge, the honest assessment of risk, and the willingness to ask hard questions even when the answers are uncertain. If you are watching this as the world sleeps around you, perhaps late at night when thoughts drift toward the edges of possibility, I invite you to leave a comment. Tell us where you are watching from and what time it is in your corner of the world. There is something quietly beautiful about knowing we are all scattered across this fragile planet, looking up at the same stars, wondering together about the same distant horizons. Now, let us begin. Let us descend together through the thin Martian sky and see what awaits us in the rust and silence below. Let us ask not whether we can dream of Mars, but whether we can survive the landing. Mars hangs in the darkness ahead, a rusty sphere marked by ancient river valleys and polar ice caps that glisten faintly in the distant sunlight. After 6 months of journey through the radiation-soaked void, this world represents both destination and challenge. But before we can stand upon its surface, before we can plant flags or establish colonies, we must first solve a riddle that has confounded engineers for decades. Mars possesses an atmosphere that exists in a cruel middle ground, a phenomenon so paradoxical it seems almost designed to thwart human ambition. The atmosphere of Mars measures only 1% the density of Earth's. To comprehend what this truly means, imagine standing on a mountaintop 3 times higher than Everest, where the air is so thin that human lungs cannot extract enough oxygen to sustain consciousness. Then make it thinner still. This is the envelope of gas that surrounds Mars, a wisp of carbon dioxide so tenuous that spacecraft instruments can barely distinguish where space ends and atmosphere begins. And yet, this phantom atmosphere presents one of the most formidable obstacles to landing safely on the red planet. Here lies the paradox. The Martian atmosphere is thick enough to create catastrophic heating during entry, yet far too thin to provide meaningful deceleration. When a spacecraft plunges toward Mars at 12,000 miles per hour, that gossamer atmosphere becomes a wall of compressed gas, generating temperatures that can melt steel and vaporize titanium. The thin air molecules, sparse though they may be, collide with the descending craft at such velocity that they transform into plasma, a glowing sheath of superheated particles that bathes the vehicle in searing energy. This is atmosphere enough to kill through heat. But when the moment comes to slow down, to break against the inexorable pull of Martian gravity, that same atmosphere offers almost nothing. The techniques that work reliably on Earth, parachutes unfurling like great flowers to catch the thick air, become exercises in futility at Mars. A parachute designed for Earth expects to encounter air molecules in abundance, billions upon billions pressed together by our planet's substantial gravity. On Mars, those molecules are scattered, sparse, insufficient. The parachute deploys into near vacuum, billowing outward with grace but grasping at phantoms, slowing the craft by increments, when what is needed is dramatic deceleration. Even if parachutes could function effectively in Mars's thin atmosphere, they face another insurmountable challenge. By the time atmospheric density increases enough for a parachute to deploy without shredding itself, the spacecraft is still traveling at supersonic speeds, thousands of miles per hour. Velocities at which impact with the surface would be instantaneous and absolute. The parachute opens, catches what little air exists, and the craft continues its deadly descent, slowing from catastrophic to merely lethal speeds. This is not landing. This is controlled falling with an inadequate brake. NASA understands this cruel mathematics intimately. Every successful Mars lander has been a masterwork of precision engineering, threading an impossibly narrow needle between too much heat and too little deceleration. The Spirit and Opportunity rovers weighed less than 400 pounds each. Curiosity, the largest rover ever landed on Mars, tipped the scales at just under 1 ton. These missions succeeded through extraordinary measures. Heat shields to survive the plasma inferno, parachutes deployed at exact altitudes, and ultimately rocket engines firing in a desperate final braking maneuver. Even with all this technology, the margin for error measured in fractions of seconds and single-digit percentages of velocity. Starship proposes something incomprehensibly more ambitious. This vehicle, fully loaded with cargo and life support systems necessary for human survival, would weigh over 100 tons. Not 1 ton, not 10, 100. This is not an incremental increase in difficulty. This is a different universe of engineering challenge entirely. Every kilogram of mass requires more braking force. Every additional ton demands more heat dissipation during entry, more atmospheric drag that isn't there to provide, more propellant for final descent engines. The mathematics scale exponentially, not linearly. The Martian atmosphere does not care about human ambition. It exists in its thin state, neither thick enough to help nor absent enough to ignore, presenting a boundary condition that has thus far permitted only the smallest robotic explorers to reach the surface intact. To land something the mass of Starship would require solving problems that exist at the very edge of physical possibility, perhaps beyond it. This is the first great barrier, the atmospheric riddle that must be answered before any other challenge can even be addressed. In the silence of space, Mars waits, wrapped in its paradoxical veil, both welcoming and forbidding, both reachable and impossibly distant. As Starship approaches Mars after months in the void, the planet grows from a reddish point of light to a looming world. But this moment of arrival carries with it a violence that few truly comprehend. The spacecraft is not gently descending. It is plummeting toward the surface at velocities that turn physics itself into an adversary. Entry into Mars' atmosphere begins at approximately 12,000 miles per hour, roughly 7.5 kilometers per second. This is not merely fast. This is a speed at which air becomes plasma, where the boundary between spacecraft and atmosphere transforms into a region of incandescent fury. To understand the magnitude of this challenge, consider the return of astronauts from the International Space Station. When a capsule re-enters Earth's atmosphere, it arrives at roughly 17,500 miles per hour, protected by a heat shield designed for precisely that velocity and that atmospheric density. The shield chars, ablates, and carries away heat in a controlled erosion. Engineers have refined this process over decades. The mathematics are well understood. The materials are proven. But Mars presents an entirely different equation. Starship arrives at the Martian atmosphere traveling at interplanetary speeds, not orbital speeds. The kinetic energy that must be dissipated is immense, yet Mars's atmosphere is only 1% as dense as Earth's. There is not enough air to slow the vehicle gradually, but there is enough to generate catastrophic heating. This paradox defines the entire entry challenge. The heat shield system designed for Starship consists of thousands of individual hexagonal tiles, each engineered to withstand extreme temperatures, while remaining light enough for a vehicle that must also launch from Earth. These tiles evoke memories of the space shuttle, which pioneered the concept of a reusable thermal protection system. The shuttle's tiles were marvels of engineering, made from silica fibers so porous they could be held bare-handed moments after glowing red hot. Yet they were also fragile, easily damaged, and required meticulous inspection before every flight. The loss of Space Shuttle Columbia in 2003 demonstrated what happens when even a single tile fails. During launch, a piece of foam struck the leading edge of Columbia's wing, damaging the heat shield. Upon re-entry, superheated plasma penetrated the wing's interior, and the vehicle disintegrated over Texas. 7 astronauts died not from an explosion or systems failure, but from a compromised heat shield. Starship's tiles are different in composition and design, engineered to be more robust, more reusable. But the principle remains the same. Each tile must maintain its integrity, must remain bonded to the spacecraft's skin, must protect the aluminum structure beneath from temperatures exceeding 2,500 degrees Fahrenheit. The margin for error is measured in fractions of an inch, a gap between tiles, a crack in the surface, a weakened bond. Any of these could allow heat to reach the underlying structure, initiating a cascade of failure that unfolds in seconds. Now consider the unique challenge Mars introduces: dust. The Martian surface is covered in fine, abrasive particles, carried aloft by dust storms that can envelop the entire planet for months. This dust is not like Earth's soil. It is electrostatically charged, clinging to surfaces with stubborn persistence. It is sharp at microscopic scales, grinding away at materials with relentless patience. When Starship lands on Mars, when it sits on the surface for weeks or months while propellant is manufactured for the return journey, this dust will settle upon every surface. It will infiltrate gaps. It will coat the heat shield tiles. And when Starship launches again, accelerating upward through the thin Martian atmosphere, that dust will scour the tiles, eroding their protective coatings, creating microscopic damage that accumulates with each mission cycle. Unlike the shuttle, which returned to Earth after each flight for exhaustive inspection and refurbishment, Starship on Mars must operate with minimal ground support. There are no technicians to examine each tile with magnifying instruments. There are no facilities to replace damaged sections. The spacecraft that carries humans back to Earth must do so with a heat shield that has already endured landing, months of exposure to Martian conditions, and the stresses of launch, all without comprehensive inspection or repair. The tiles must remain intact, not through a single mission profile, but through multiple atmospheric entries, ascents, and prolonged surface exposure. Perhaps the most unsettling aspect of this challenge is the absence of precedent. Humanity has never sent astronauts through an interplanetary entry. Every crude atmospheric entry in history has been from low Earth orbit or from lunar return velocities. Apollo astronauts returning from the Moon entered Earth's atmosphere at roughly 25,000 miles per hour, the fastest humans have ever traveled during re-entry. But they did so protected by an ablative heat shield that was designed to burn away, and they plunged into Earth's dense atmosphere, which provided robust deceleration. Mars offers neither the forgiving density of Earth's air, nor the option for single-use ablative protection. Starship must survive, remain intact, and be ready to return its occupants across millions of miles of space. The inspection problem compounds these concerns. On missions to the Moon, astronauts could perform extravehicular activities in lunar orbit to examine their spacecraft before the return journey. The Apollo command module's heat shield could be visually verified, but on the journey to Mars, no such inspection is possible for the heat shield tiles that cover Starship's belly and sides. The crew cannot exit the vehicle during the interplanetary cruise to examine tiles for damage. If a micrometeorite impact during the months-long transit compromises even a small section of the heat shield, that damage will remain undetected until entry begins. By then, it is far too late. History whispers caution. The loss of Columbia was not the only heat shield tragedy. Soviet cosmonaut Vladimir Komarov died in 1967 when Soyuz 1's parachute failed to deploy properly, but re-entry heating had already compromised multiple systems. Later investigations of close calls revealed how often thermal protection has been tested to its absolute limits. Each time astronauts return from space, they are trusting their lives to materials that must perform flawlessly under conditions that would vaporize steel in seconds. The heat shield is not merely a component. It is the thin boundary between survival and obliteration, between controlled descent and catastrophic disintegration. For Starship, this boundary must hold not once, but repeatedly, across conditions never before tested with human lives at stake. In the silence of approach, as Mars grows from a distant hope to an imminent reality, the tiles remain the silent guardians. Whether they will prove resilient enough for the challenge ahead is a question that cannot be answered with simulations alone. Only the fire of entry will reveal the truth. As Starship descends toward Mars, carrying its precious cargo of human life, it must perform what SpaceX engineers call a belly flop maneuver. The name sounds almost playful, reminiscent of summer days at the pool. But this is no casual dive. This is a 50-meter tall skyscraper, falling horizontally through an alien atmosphere at thousands of miles per hour, before flipping upright in the final seconds to land on engines that must ignite perfectly or doom everyone aboard. The concept is elegant in its simplicity. Unlike traditional spacecraft that descend vertically, nose first, Starship rotates to fall belly down, presenting its entire broadside to the Martian atmosphere. This orientation maximizes surface area, creating enormous atmospheric drag without burning vast quantities of fuel. It is, in essence, using Mars itself as a brake, allowing the thin atmosphere to do work that would otherwise require tons of propellant. The spacecraft falls like a skydiver, arms and legs spread wide, controlling its descent through subtle shifts in position. But elegance on paper transforms into terror in practice. The maneuver unfolds in stages, each one dependent on precise timing and flawless execution. After surviving the initial heat shield entry, Starship must rotate 90 degrees, transitioning from vertical to horizontal. As it falls through the tenuous Martian air, small fins at the nose and tail make constant adjustments, keeping the spacecraft stable as it plummets. The atmosphere here is only 1% as dense as Earth's, which means these control surfaces must work much harder to have any effect at all. Every correction requires larger movements, more dramatic shifts in angle. The margins for error narrow with each passing second. Then comes the flip. Mere seconds before impact, when the Martian surface fills every window with rust-colored urgency, Starship must rotate back to vertical. The Raptor engines must ignite. The descent must transform from a controlled fall to a powered landing, all while the spacecraft transitions from horizontal to upright. This entire sequence happens in moments. If the rotation begins too early, the engines will waste fuel fighting gravity. Too late, and there is no time to slow down. The timing must be measured not in seconds, but in fractions of seconds. Milliseconds become the difference between landing and catastrophe. SpaceX has performed this maneuver successfully on Earth. We have watched test flights where Starship executed perfect belly flops, rotated gracefully, and landed with mechanical precision. But Earth is not Mars. Earth's atmosphere is a thick cushion that provides predictable resistance. Earth's gravity is stronger, making the physics of the flip more forgiving. And perhaps most crucially, Earth test flights carry no human passengers who have just spent 6 months deteriorating in the void of space. Consider what this maneuver demands of the human body. After half a year in microgravity, astronauts are fundamentally changed. Their cardiovascular systems have adapted to an environment without up or down. Their muscles have atrophied. Their bones have shed density. Their inner ears, responsible for balance and spatial orientation, have recalibrated to weightlessness. Now suddenly, they are subjected to intense G-forces as the spacecraft rotates and decelerates. The belly flop itself generates lateral forces that push bodies sideways. The flip rotation creates angular acceleration. The final engine burn produces vertical deceleration that can reach several Gs. On Earth, a trained astronaut in peak physical condition might tolerate these forces with discomfort but no lasting harm. But these will not be peak condition astronauts. These will be weakened, disoriented individuals whose bodies have forgotten what weight feels like. The sudden return of gravity, combined with the violent motions of the flip maneuver, could cause loss of consciousness. It could trigger cardiac arrhythmias in hearts that have spent months pumping blood in 0G. It could induce severe vertigo that leaves crew members unable to perform emergency procedures if something goes wrong. And things can go wrong in ways that Earth tests cannot fully reveal. The Raptor engines that must ignite for the flip are sophisticated machines, among the most advanced rocket engines ever built. They burn liquid methane and liquid oxygen, producing tremendous thrust with remarkable efficiency. But they have spent 6 months in space, exposed to radiation, thermal cycling, and the subtle degradation that affects all machinery in the cosmic environment. These engines must start cold. They must start instantly. There is no second chance, no opportunity to troubleshoot if one fails to light. Starship's landing depends on multiple Raptor engines firing simultaneously. The current design uses 3 engines for the landing burn, providing redundancy. If one fails, the others can theoretically compensate. But can they compensate during a flip maneuver, when the spacecraft is rotating and every engine's thrust vector matters for both slowing down and maintaining orientation? A single engine failure during the flip could cause the spacecraft to tumble, to rotate incorrectly, to slam into the Martian surface at an angle that no structure could survive. The mathematics of the maneuver allow for almost no deviation. Engineers have calculated trajectories down to decimal points, modelled atmospheric conditions with sophisticated simulations, and tested hardware in conditions meant to approximate Mars. But Mars is not a simulation. The Martian atmosphere varies with seasons, with dust storms, with daily temperature swings that alter air density. The surface winds, though weak by Earth standards, can still affect a falling skyscraper with enormous surface area. The landing site may have terrain features, rocks, or slopes that weren't visible in orbital photography. Perhaps most troubling is the psychological dimension. The crew, already stressed by months of confinement and the knowledge that they are farther from help than any humans in history, must now trust their lives to a maneuver that defies intuition. They must watch through windows as their spacecraft falls sideways, must feel the sickening rotation as it flips, must experience seconds that stretch into subjective eternities while wondering if the engines will light. There is no ejection system, no escape pods, no emergency parachutes. They are passengers in a falling tower, hoping that mathematics and engineering have accounted for every variable. SpaceX chose the belly flop because alternatives demanded too much fuel, making the entire Mars mission economically impossible. The choice was driven by necessity, not preference. It is a solution born from the constraints of rocket equations and payload limits. In that sense, it is brilliant. It makes possible what would otherwise be fantasy. But brilliance does not guarantee survival. The maneuver works on Earth because we have gravity and atmosphere in proportions that forgive small errors. Mars offers no such forgiveness. Its thin air provides just enough resistance to make the belly flop viable, but not enough to make it comfortable. Its gravity is strong enough to kill, but weak enough to alter the dynamics we have practiced. Every parameter sits at the edge of what is possible, leaving almost no room between success and silence. As we contemplate Starship's descent, falling belly down through the Martian dusk, we must ask ourselves whether elegant engineering is sufficient when the cost of failure is measured in human lives. Is this maneuver a testament to human ingenuity, or is it a gamble we are taking because we have not yet imagined a safer alternative? By the time a starship full of people reaches Mars, something strange has happened to the engines they depend on. They have become ghosts. The same Raptor engines that roared to life on launch day, bathing the pad in fire and thunder, will have been silent for 6, perhaps 9 months. No flame, no movement, just metal and plumbing drifting through a darkness so cold it makes Antarctica seem warm. On Earth, engines are living things. They're inspected, tested, warmed, and watched. Technicians listen to them, measure them, and take them apart when something feels wrong. But in the deep quiet between planets, the engines sleep unattended. No hands touch them. No eyes see them. The only witness is the vacuum itself. For Starship to land on Mars, that silence must end in a single, perfect moment. As the ship slices into the upper edge of the Martian atmosphere, it will fall belly first, using drag to slow down, trading speed for heat and heat for friction in the thin, rusty air. But at some point, high above the rocks and dust and frozen valleys below, aerodynamics is no longer enough. Gravity still pulls. Velocity still remains. The difference between a landing and an impact becomes a question with a mechanical answer. Will the engines wake up? In the emptiness between worlds, temperature is a strange concept. There is no air to feel cold. There is only radiation and the way materials give off and absorb heat. Parts of the spacecraft in direct sunlight can bake hotter than boiling water. Parts in shadow can sink to hundreds of degrees below zero. Over months, this constant quiet cycling of temperature seeps into everything: wires, seals, valves, sensors. Raptor engines are intricate sculptures of stainless steel and exotic alloys. Inside them, turbopumps must spin at tens of thousands of revolutions per minute. Valves must open at exactly the right microsecond. Sensors must read pressures and temperatures precisely, feeding computers that decide whether the engine is healthy or dying. In deep space, none of these parts are operating. They are simply enduring. Lubricants slowly shift and thin. Tiny clearances in bearings and seals can change as metals expand in the sun and contract in the shade, over and over again. Electrical connectors, crimped and tightened on Earth, experience ionizing radiation that can subtly damage insulation and electronics. Micrometeoroids, grains of dust moving faster than bullets, occasionally strike, each one a tiny, random test of the ship's armor. On Earth, we call these effects aging and wear. In space, over interplanetary timescales, they become something else: uncertainty. Then there is the propellant itself. Starship carries liquid methane and liquid oxygen, both stored at cryogenic temperatures. Cold enough to turn air into liquid, cold enough to make most materials brittle. To keep these tanks from warming and boiling away their contents, engineers rely on careful insulation, clever tank design, and sometimes active cooling. But no insulation is perfect. Over months, a little heat always leaks in. This is more than just a bookkeeping problem of how much fuel is left. As methane and oxygen slowly warm and cool, layers in the tanks can stratify. Gas bubbles can form and move unpredictably. Sloshing can shift the center of mass. Valves that were meant to handle liquid might suddenly swallow pockets of vapor. An ignition system designed for steady, well-behaved flows might be asked to cope with a chaotic mix of phases: part liquid, part gas, part frost. On the ground, such conditions would be tested, characterized and controlled. In orbit around Mars, there is only one test that actually matters, the one that happens when the ship is already falling. The challenge is not just to light one engine, it is to start the exact engines needed, at the exact time, in the exact sequence, in an environment that no human technician has ever touched. Every step in this process is a chain. Sensors must correctly detect propellant pressures and temperatures. Computers must interpret those signals, comparing them to models written months or years earlier. Valves must open and close with microsecond precision. Pumps must spin up without seizing. Combustion chambers must ignite without exploding. If any one of these links fails, the engine might refuse to start, or worse, it might start badly. On Earth, a bad start is a lesson. The engine can be shut down, examined, rebuilt. Data can be gathered. Teams can run simulations, redesign parts, rewrite code. There is always another test, another chance. At Mars, there is no abort tower to pull the crew away from danger, no emergency runway on a quiet desert plain, no rescue helicopter waiting just over the horizon. If the main braking burn fails, Starship does not simply try again. Gravity does not pause while troubleshooting occurs. The ground keeps rising. Time keeps shrinking. Designers can add redundancy. Instead of one engine, there are several. Instead of relying on a single ignition pathway, there may be backup sparkers, fallback valves, alternate start profiles. Redundancy is humanity's favorite answer to risk, but redundancy in rocketry is subtle. Multiple engines share common plumbing, common tanks, common control systems. A fault in tank pressurization will not care how many engines you have. A tiny crack in a manifold, slowly growing during months of thermal cycling, can feed several chambers at once. A software bug that misreads a sensor does not just silence one engine. It can keep them all asleep. Even if some engines do light, their combined thrust must align precisely with the ship's center of mass. If one engine underperforms, or a nozzle is slightly damaged, the imbalance can create torques and spins at the worst possible moment. The computers can try to compensate, throttling one engine, gimballing another, dancing a complex ballet of vector and force. But there is a limit to how much imbalance can be tamed by clever math and fast actuators, especially when the vehicle is large, heavy, and plummeting through a thin, unforgiving atmosphere. Layers of vibration and stress have already marked each engine long before this moment. The violence of liftoff, the shaking of max Q as the ship punched through the air on departure, the subtle flexing of the structure with every orbital maneuver. Materials remember. Tiny, invisible microcracks can slowly propagate, like faults deep within a mountain range, waiting for the right combination of stress to release. The re-entry itself adds one more trial. Even in Mars's thin air, the front of the ship will heat. Shock waves will wrap around the hull. Local turbulence can send shudders and rumbles through the structure, rattling every pipe and bracket. At the end of this, the engines are asked to perform an act of precision, a controlled, smooth ignition with finely tuned thrust, as if none of the chaos before it ever happened. In concept, it is simple. Engines that work on Earth can work at Mars. Physics is the same, methane is the same, oxygen is the same. In practice, the time in between, the months of quiet exposure to space, the slow drift of temperatures, the invisible accumulation of small stresses, creates a question we have never fully answered at human scales. How perfectly can we trust machinery that has slept unattended between worlds? This is not a condemnation of Starship, or of SpaceX, or of ambition itself. It is a reminder of the frontier we are entering. We have restarted engines in space before. Apollo did it. The space shuttle did it. Probes to Jupiter and Saturn did it countless times. But each of those systems carried its own margins, its own environment, its own level of human risk. With Starship, the scale changes, the number of engines, the length of the journey, the cryogenic nature of the fuel, the speed of arrival, and above all, the stakes, not just data and hardware, but lives. To land gently on Mars, humanity will have to do something both technical and philosophical. We will have to look at a cluster of dormant metal bells, coated in dust and frost, and decide that they will awaken exactly when we ask them to. We will strap ourselves to cold machinery, cross the emptiness between planets, and place our futures in the moment when fire returns to steel. The journey from Earth to Mars is often described in terms of distance and time. 6 months, tens of millions of miles, a transfer orbit carved elegantly through the void. But for the human body, that journey is not a line on a trajectory plot. It is a slow passage through an invisible storm. The moment Starship leaves low Earth orbit, it crosses an unseen border. Behind it, the invisible cocoon of Earth's magnetic field, which has sheltered life for billions of years. Ahead, a realm where radiation arrives not filtered, but raw. On Earth's surface, the planet's magnetic field and thick atmosphere work together like layers of armor. High-energy particles from the Sun and from distant galaxies are deflected, scattered, absorbed. What reaches us is a whisper of what is really out there. In deep space, far from this protective shield, that whisper becomes a constant, relentless hail. This hail is made of cosmic rays, fragments of atoms accelerated to nearly the speed of light by supernova explosions, black holes, and events so powerful they reshape entire regions of the galaxy. To us, they arrive as solitary travelers, but each carries the energy of a microscopic bullet. They pass through aluminum, plastic, steel, even flesh, leaving behind tiny scars in everything they touch. Around Earth, the magnetosphere bends many of these particles away. On the journey to Mars, there is no such guardian. Starship, with its stainless steel hull, becomes the only shelter between the crew and the cosmic tide. Steel feels strong to us, cold, solid, impenetrable. But to a high-energy cosmic ray, it is more like a veil than a wall. When these particles strike the hull, some are stopped, others punch straight through, and many do something more troubling. They collide with atoms in the metal, shattering them and spraying out a shower of secondary particles, neutrons, protons, fragments of nuclei, that then continue into the ship's interior. The very material meant to protect can, under the assault of cosmic rays, become a source of new radiation. This is one of the paradoxes of shielding in deep space. Heavier materials block some threats, but can create others. Engineers can add water tanks, fuel, or supplies to certain areas, building improvised shelters where the crew can retreat during peaks in radiation. Water and hydrogen-rich materials are very good at slowing charged particles, but mass is limited. Every kilogram of shielding is a kilogram that cannot be propellant, payload, or life support. Starship's sleek steel skin, so impressive for rapid construction and thermal resilience, is not a fortress. It is a compromise. Cosmic rays are only one half of the gauntlet. The other half comes from our own star. The Sun, usually a gentle disk of light in our sky, is in truth a roiling fusion furnace, endlessly boiling and erupting. Most days, it bathes the solar system in a steady wind of particles, energetic but manageable. Yet at unpredictable intervals, the Sun changes temperament. It unleashes solar particle events, bursts of high-energy protons and heavier ions hurled outward at astonishing speeds. On Earth, These storms may paint the sky with auroras, shimmering curtains of green and red. In deep space, with no magnetic field to divert them, they can turn a spacecraft into the center of an invisible downpour. Within hours, radiation levels can spike from uncomfortable to dangerous, then potentially to lethal. For astronauts in low Earth orbit, like those on the International Space Station, the planet's magnetic field still softens the blow. For a crew halfway to Mars, there is nothing but the thickness of the hull and whatever ad hoc storm shelter they've prepared. If a major event aligns poorly with their trajectory, the crew could receive a dose of radiation that, on Earth, would only be seen in the aftermath of nuclear accidents. We do not yet fully know how often such worst-case alignments might occur over many Mars missions. We can forecast the Sun's general cycles, but not each individual storm. It is like planning a 6-month hike across open terrain, where thunderstorms are not just wet and loud, but occasionally sharp enough to pierce bone. Radiation does not announce itself. It carries no sound, no color, no immediate sensation. The crew will not feel the cosmic rays as they pass, or hear the solar storm as it sweeps over the hull. Instead, radiation works in silence, at the smallest scales, altering molecules one by one. DNA is one of its primary targets. The double helix inside each cell is not a rigid ladder, but a delicate structure that is constantly repaired by the cell's own machinery. On Earth, our bodies handle this maintenance with quiet efficiency. In deep space, the number of breaks, crosslinks, and mutations increases. Most are repaired, some are not. Over months, the cumulative effect is a slow accumulation of damage that can raise long-term cancer risk and interfere with normal cell function. The nervous system, with its intricate web of neurons, is also vulnerable. Animal studies and research on particle accelerators suggest that high-energy charged particles can alter the way brain cells communicate, inflame delicate tissues, and subtly shift the chemistry that underlies memory, attention, and mood. Not all scientists agree on the exact magnitude of these risks for Mars-class missions. Some models suggest that with careful shielding and mission timing, the effects could be kept modest. Others warn that even one long journey might have measurable cognitive consequences. For a crew that must pilot and land a massive vehicle on an alien world, this uncertainty is not academic. Mars landing is already one of the most demanding phases of the mission. Timelines are tight, procedures complex, and windows for correction narrow. If radiation has even slightly dulled reaction times, impaired memory, or increased fatigue, the difference may emerge at precisely the moment when clarity is most needed. Radiation also threads itself through the cardiovascular system. Exposure over months appears to increase inflammation in blood vessels, alter the behavior of heart muscle cells, and accelerate processes similar to aging. On Earth, such changes might contribute to heart disease over years or decades. On a Mars mission, they might translate into subtle reductions in endurance, irregular heart rhythms, or reduced capacity to withstand stress. When combined with microgravity's own toll on blood distribution and heart strength, the result is a body that may be less resilient just when it must perform at its peak. All of these effects on DNA, the brain, the heart, are cumulative. None arrive with a single dramatic event. They are more like the slow weathering of stone by wind and rain, and they do not occur in isolation. They layer atop sleep disruption, confined habitat stress, changes in circadian rhythm, and the physiological strain of weightlessness. By the time Starship reaches Mars after 6 months in deep space, its crew will not be the same people who left Earth, at least not biologically. They may carry microscopic scars in their DNA, subtle shifts in their neural circuits, trace inflammations in their vessels. Most will be invisible, detectable only with instruments and years of follow-up. But some may appear in everyday ways: slower mental arithmetic, reduced multitasking, increased irritability, or simply a deeper, more inescapable fatigue. Now imagine aligning that state with the demands of Mars entry, descent, and landing. A planet with a thin, deceptive atmosphere, a vehicle the size of a small skyscraper, a landing sequence that must be executed with unerring timing, turning the ship, firing engines, managing fuel slosh, correcting for winds and dust. There is little room for hesitation, less for confusion. In principle, much of this can be automated. Computers can guide, correct, and even fully control the descent. But humans remain the ultimate backup, the ones who must understand what is happening, decide when to intervene, and respond to the unexpected. If a sensor fails, if a valve sticks, if a landing leg does not deploy exactly as planned, the crew must interpret and act. We often imagine these astronauts as the best Earth can offer: supremely trained, mentally sharp, physically robust, and they likely will be. Yet the radiation gauntlet between here and Mars guarantees that upon arrival they will also be something else: survivors of an invisible storm, carrying within them the quiet evidence of that passage. For Starship, and for any crewed Mars mission, this is not an abstract medical detail. It is a direct contributor to landing safety. A weakened, subtly impaired crew facing the most dangerous minutes of the journey is a risk multiplier written not in engineering diagrams, but in biology. To cross the space between worlds is to bring the human body into an environment for which it was never shaped. Steel hulls, storm shelters, mission timing, and clever trajectories can all soften the blow. But they do not erase it. The radiation of deep space is patient. It works on the smallest scales, over months that feel uneventful, until one day the ship arrives at Mars, and we discover what 6 months in the cosmic tide have truly done to those who must now land. The journey to Mars is not measured only in miles or months. It is also measured in what is quietly taken from the human body along the way. From the moment a crew leaves Earth's gravity, something subtle begins. Muscles, once used to pushing against the pull of a planet, no longer need to work as hard. Bones that have carried weight since birth suddenly float, unburdened. At first, this feels like freedom. But in biology, freedom from effort often has a price. In microgravity, the body is an efficient negotiator. It asks a simple question: if this strength is no longer needed, why maintain it? Over 6 to 9 months between worlds, that negotiation becomes a slow surrender. The powerful muscles of the legs and back, built for standing and walking, gradually weaken. The deep postural muscles that hold us upright on Earth begin to fade. Even the heart, a tireless muscle, reshapes itself, learning that it no longer needs to pump quite as hard. Bones join this quiet revolt. On Earth, every step sends tiny shocks through our skeleton. These impacts tell our bones to stay dense and strong. In space, that signal falls silent. Without the daily dialogue of weight and resistance, bone cells shift balance. The builders fall behind. The dismantlers take the lead. Calcium seeps from the skeleton into the bloodstream, and from there, out of the body. Over months, the scaffolding of the human form grows thinner, more fragile, as if the body is slowly forgetting gravity ever existed. We know this not as speculation, but from decades aboard the International Space Station. Astronauts there, even with disciplined exercise, can lose around 1 to 2% of their bone mass per month in certain regions. Hip bones, spine, and legs, exactly the structures we rely on when we stand, fall, or try to escape danger. Muscles can shrink by 20% or more on long-duration flights. The body is not failing. It is adapting to a new environment. But those adaptations become liabilities the instant we return to a world with weight. To fight this, space agencies have built a gym in orbit. On the ISS, astronauts spend about 2 hours every day exercising. Treadmills with harnesses pull them toward the belt, simulating weight. Resistance machines use vacuum cylinders instead of iron plates, letting them lift heavy loads in weightlessness. Cycling machines keep the heart and lungs engaged. These methods help, but they are not a cure. Even with perfect discipline, some loss of strength and bone density persists. And the ISS is relatively close to Earth, a few months away at most. If something goes wrong with a crew member's health, return is difficult but not impossible. A Mars crew has no such option. Once they are en route, there is no turning back, no emergency evacuation. The body that arrives must be ready to live there, or to survive failure without the safety net of home. And this leads us to a hard question. What happens when a body that has been floating for 6 to 9 months suddenly has to land on another planet? Elon Musk's Starship concept imagines a large vehicle descending through the thin Martian atmosphere, engines firing, dust swirling, the ship turning its fall into a controlled, upright landing. But inside that sleek maneuver is a very old challenge: acceleration. Even a gentle landing involves changes in speed. Small spikes of G-forces press bodies into seats, shake bones against straps, demand that muscles brace and stabilize. For a person fresh from Earth, this is uncomfortable, but tolerable. For a person whose spine has flattened slightly, whose leg muscles have thinned, whose cardiovascular system has grown used to effortless circulation, each jolt is amplified. A rough touchdown is no longer just a design concern. It becomes a medical risk. We have seen hints of this on Earth. Cosmonauts returning from long stays on space stations have sometimes needed to be carried from their capsules. Not because they lack willpower, but because standing suddenly in Earth gravity after months in orbit can be disorienting and exhausting. Blood, which floated evenly in microgravity, surges downward. Vision can dim. Some astronauts report feeling as if their bodies are made of stone. Their first steps back on Earth can be more like learning to walk again than like coming home. Now imagine that same fragile moment, not on a recovery ship in the Pacific, surrounded by doctors, but on the surface of Mars, in freezing air, with dust storms in the distance, and no rescue teams waiting nearby. When Starship lands, if it lands, its crew cannot simply lie there and rest. Every Mars mission architecture, whether from NASA, SpaceX, or other planners, shares a common assumption. Astronauts must be functional almost immediately. They may need to inspect their vehicle, check for leaks, assess the integrity of landing legs. They may need to deploy power systems, confirm that life support is stable, or respond to any number of unpredictable emergencies. On Earth, first responders are minutes away. On Mars, the first responders are you. Historical data tell us that this expectation is ambitious. Many returning astronauts need hours, sometimes days, to feel fully stable again in Earth gravity. They practice standing tests before flight, tilted tables, rapid posture changes, to help predict who might be vulnerable to fainting or dizziness. Even then, not everything can be anticipated. The human body, like any complex system, has thresholds that only become visible when they are crossed. Mars complicates this in an unusual way. Its gravity is only 38% of Earth's. On paper, this seems like mercy. Everything is lighter, jumps are higher, steps are easier. But for a deconditioned body, 38% is not nothing. It is still a constant downward pull, still a force that must be resisted with bone, tendon, and muscle that have been on sabbatical for months. From one perspective, Mars' gravity is a halfway house between weightlessness and Earth. From another, it is the worst of both worlds, strong enough to cause falls and injuries, yet not strong enough to fully signal bones to rebuild to Earth-normal strength. A crew may regain some function in this lower gravity, but their skeleton may never fully recover while they remain off-world. Over years, this raises questions about fractures, mobility, and the risk of long-term disability on another planet. Scientists and engineers have proposed solutions, rotating spacecraft to create artificial gravity through centrifugal force, short-arm centrifuges inside the ship, where astronauts could spin for an hour a day to remind their bodies what down feels like. Improved exercise devices that more closely mimic the loads of walking and running under real weight. Nutritional changes and drugs that might slow bone loss or stimulate new growth. Each of these ideas holds promise, but none has yet been proven in the exact conditions a Mars mission would require: years away from Earth, continuous use, limited maintenance, and the psychological strain of confinement and distance. In the equations of a mission plan, these unknowns are more than academic. They decide whether the people who step onto the Martian surface will be explorers or patients. The paradox is stark. We know how to send machines to Mars, to land them, to rove, to drill, to analyze. Robots do not suffer from atrophy or brittle bones. They do not need to stand up after landing. Humans do. The very thing that makes a Mars colony meaningful, living, breathing people, is also what makes it fragile. In the grand narrative of space exploration, rockets and engines often take center stage. Yet in the quiet corridors of mission design, another question lingers, just as important and far more personal. After half a year of falling through the void, will our bodies still be strong enough to rise in a new world? As we trace this question forward, we find ourselves at the boundary between aspiration and biology. The dream of walking on Mars does not end with touchdown. In many ways, that is where the hardest part begins. On Earth, we choose landing sites with the arrogance of familiarity. We have maps, satellite images, aircraft surveys, and, if needed, a person can simply walk the ground. We know where the cliffs are, where the sand is soft, where the bedrock lies close to the surface. On Mars, we choose from orbit, and we guess, from more than 100 miles above, the surface of Mars looks surprisingly detailed. Instruments like HiRISE can pick out features as small as a coffee table. We can see dunes, boulders, ancient riverbeds. We can color-code slopes, estimate rock abundance, and trace the outlines of craters that have slept for billions of years. But this clarity is an illusion of safety, because the closer you get to Mars, the more the map dissolves into uncertainty. A Starship-sized vehicle does not land with the precision of a dart in a bullseye. It arrives in an ellipse of probability, a landing zone measured in hundreds of meters, perhaps more, depending on how the atmosphere behaves that day. And within that footprint, our knowledge breaks down. Between the pixels of orbital imagery, there are gaps, small boulders, shallow depressions, uneven layers of dust that only reveal themselves when it is far too late to steer away. NASA's robotic landers have threaded this needle with meticulous care. Curiosity and Perseverance use sky cranes, parachutes, and radar to pick relatively safe flat ground after years of analysis and simulation. Even then, engineers held their breath as each rover descended, knowing that a single hidden rock could turn triumph into wreckage. Those machines weighed about a ton. Starship, with a full crew and cargo, will weigh hundreds of tons when it tries to stand on alien soil. The margin for error does not grow with the vehicle. It shrinks. Mars itself is not a static backdrop waiting politely for our arrival. It is alive with motion, thin as its air may be. Across the plains, dust devils wander like ghostly tornadoes, spinning columns of fine powder that stretch hundreds of meters into the sky. Orbiters have watched them carve dark tracks across the ground, erasing and rewriting the surface in slow, swirling script. Most of the time, these dust devils are harmless, but their paths are chaotic. They rise and die without warning, driven by pockets of warm air and faint pressure changes. A landing zone surveyed months before could be subtly reshaped by their passage. Dunes migrate grain by grain. Dust blankets rock or scours it bare. Local weather on Mars is not a gentle background. It is a restless painter, constantly retouching the canvas. Then there are the regional storms, hazy veils of dust that can spread over hundreds of kilometers. And, some years, the planet-wide events, when Mars wraps itself in a shroud of fine particles, turning day into rust-colored twilight. For a robotic mission, these storms are an operational challenge. For a human lander, depending on engines and sensors, they become something more serious. Dust in the air can confuse laser rangefinders and cameras. Dust on the ground can conceal hazards. And dust in the engine plume can rise in choking clouds, reflecting radar signals and hiding the surface just when you need to see it most. In simulations, the landing looks smooth. In reality, the last few seconds might unfold inside a storm of your own making. Beneath that dust lies another unknown, the regolith itself. Mars soil is not soil in the way we know it on Earth. It is a mixture of broken rock, oxidized minerals, and finely ground particles that may cling, flow, or collapse in ways we have only glimpsed through robotic wheels and drill bits. We have tasted Mars with tiny metal scoops, pressed it with rover tracks, and drilled a few centimeters into its crust. But we have never slammed a skyscraper-sized vehicle down on 4 feet and asked, will it hold? In some regions, the regolith might be firm, supported by buried rock or ancient lava. In others, it could be deceptively soft, more like talcum powder than sand. There may be layers, a tougher crust over weaker material, that behave unpredictably under the concentrated weight of landing legs. A small robotic lander can tolerate a few centimeters of sinkage. A towering Starship, if one leg sinks more than the others, could tilt, slide, or topple. The danger is not only in what we see, but in what is hidden. A smooth-looking patch of ground from orbit might hide shallow craters, bowls filled with loose debris that appear flat until you stand on their rim. Gentle slopes can be mismeasured by a fraction of a degree, but for a tall vehicle, that fraction matters. A rock the size of a chair, invisible in the blur of descent, could be exactly in the wrong place under a landing foot. Mars Reconnaissance Orbiter has transformed our understanding of the planet, but even it cannot map every rock, every ripple, every hollow. The resolution of the best images is still measured in tens of centimeters per pixel. Anything smaller is averaged into a color, a brightness, a suggestion. For human landing systems, Those suggestions must become certainty, and we are not there yet. Complicating all of this is a constraint that no engineering brilliance can remove. Distance. During landing, Mars and Earth do not share a conversation. They exchange delayed messages. Depending on where the planets are in their orbits, radio signals can take between 4 and 24 minutes to travel one way. By the time a human controller sees a problem on a telemetry screen, the landing is already over. The vehicle is either safe on the ground, or it is not. This is why every Mars lander, from Viking to Perseverance, has entered what Mission Control calls 7 minutes of terror, or entry, descent, and landing, with its fate sealed in code. Commands are preloaded. Algorithms run on their own. The craft senses, decides, and acts faster than any human could hope to respond across millions of kilometers. For Starship carrying people, this reality does not change. There will be no heroic pilot yanking the controls at the last second. No test pilot's instincts smoothing out a hard landing. No ground controller calling for an abort when a dust plume obscures the radar. The crew, if they are awake, will be passengers on a fully autonomous descent, watching instruments and trusting that lines of software written months or years before have accounted for every surprise Mars can offer. Autonomous systems can be precise. They can learn, adapt, and improve. But they cannot be perfect because the world they encounter is not perfect. Sensors get dusted. Engine thrust fluctuates. The local terrain is slightly rougher than the simulation assumed. A tiny error in altitude measurement becomes a harsh impact when magnified by several hundred tons of mass. Engineers can build redundancy, cross-checks, and layers of backup logic. They can train neural networks on millions of images. They can test in deserts, in vacuum chambers, in wind tunnels. Yet, all of these are shadows of the real thing. There is no Martian proving ground on Earth where we can practice dropping a full-scale Starship into a chaos of dust, low gravity, and unknown geology. In the end, the act of landing on Mars becomes a kind of celestial gamble. Not reckless, not careless, but a gamble all the same, rolling the dice with imperfect knowledge of the table. Every grain of regolith, every hidden rock, every thin veil of dust-filled air is a reminder that mapping a world from above is not the same as knowing it from below. Orbital images are promises, not guarantees. They whisper, "This place is probably safe." They never say, "This place is utterly certain." For a robotic rover, that difference is acceptable. For a ship full of humans, it is the narrow space between a bold landing and a silent field of twisted metal on a cold, empty plain. Before we can claim Mars as a destination for people, we must first accept it as a landscape of unknowns, a place where every touchdown is not just a test of engines and metal, but of our willingness to entrust human lives to a surface we have only seen from far, far away. The journey to Mars does not end when the landing legs touch the dust. For Starship, that's only the midpoint of the story. Unlike Apollo, there is no return rocket waiting in orbit, no fully fueled ascent stage hidden under protective shrouds. The plan for coming home rests on a quiet, invisible promise that on a cold, distant world, far from any human hand, an entire fuel factory will work perfectly. This idea has a name: in situ resource utilization, or ISRU. Instead of carrying all the propellant from Earth, Starship is designed to make its own fuel on Mars, using what the planet already offers. In theory, it is brilliantly elegant. Mars has a carbon dioxide atmosphere and water locked in ice. Starship uses methane and liquid oxygen, carbon, hydrogen, and oxygen. The ingredients seem to be waiting. The reaction that ties this all together is simple enough to fit on a whiteboard. It's called the Sabatier reaction. You take carbon dioxide, CO2, from the Martian air. You combine it with hydrogen, H2, which you obtain from water ice by splitting H2O into hydrogen and oxygen. Under the right conditions, the molecules rearrange themselves. CO2 plus 4. H2 yields CH, 4 plus 2, H2O. Carbon dioxide and hydrogen go in. Methane and water come out. The methane becomes Starship's fuel. The oxygen, obtained from both the water and from other processes, becomes the oxidizer. The reaction was discovered on Earth more than a century ago, and small Sabatier systems have already been tested by space agencies, even on the International Space Station. On paper, it is almost poetic. Mars breathes out carbon dioxide. We add hydrogen extracted from ancient ice. The planet itself becomes the source of the propellant that will carry us back to Earth. But there is a difference between chemistry on a lab bench and a life-critical industrial plant running for years on another world. We have never operated a chemical factory, fully automated, millions of kilometers away, with no human technicians walking the floor, no spare parts warehouse down the road, no emergency team to respond when a valve sticks or a pump seizes in the night. We can barely keep complex refineries on Earth running smoothly, surrounded by sensors, engineers, and maintenance crews. On Mars, there is only dust, cold, and the long delay of radio waves. For Starship's vision, this factory cannot be small. A return flight demands not a few test tubes of methane, but hundreds of tons of propellant, cooled and stored as cryogenic liquids. Every kilogram of fuel must be manufactured, purified, chilled, and kept from boiling away in the thin Martian atmosphere. To do that, you need power. A lot of it. On Earth, industrial plants drink electricity from vast grids. On Mars, there is no grid. The options narrow to two main choices: nuclear reactors or giant fields of solar panels. Nuclear power offers steady energy, day and night, through dust storms and winters. But landing a reactor on Mars is not a trivial feat. It must be safe, compact, reliable, and capable of running for years without maintenance. Designs exist on paper and in prototypes from several space agencies, but no full-scale nuclear plant has ever been operated on another world. Solar power, in contrast, feels familiar. Panels unfold like metallic petals, catching pale sunlight. Yet Mars is 1.5 times farther from the Sun than Earth, and the light that reaches its surface is weaker. Dust gathers on every surface. Storms can dim the sky for weeks or longer. To power a propellant plant solely from sunlight, you would need sprawling solar farms, battery storage, and cleaning systems that work flawlessly in an environment where a single storm can erase the horizon. In both cases, nuclear or solar, the requirement is the same: years of dependable operation, with no opportunity for rescue, adjustment, or overhaul if something fundamental goes wrong. The power system is not a side project. It is the beating heart of the plan to come home. Then there is water. Mars, from orbit, looks dry and rusted. But beneath the surface, especially near the poles and in certain mid-latitude regions, we have strong evidence for abundant ice. Radar measurements, neutron detectors, and impact craters reveal layers of frozen water locked away like a planetary memory. We believe it is there. In some places, we are nearly certain. But belief is not the same as a proven, practical well. To fuel Starship, we do not just need to confirm that ice exists. We need to reach it, mine it, melt it, filter it, and feed it into electrolysis systems that split it into hydrogen and oxygen. Each step opens a new chain of engineering challenges. Drills must survive abrasive regolith. Pipes must resist clogging and freezing. Tanks must store water and gases at carefully controlled temperatures. On Earth, those challenges are routine. On Mars, they become questions without tested answers. We have never drilled meters into Martian ground and extracted tons of clean water continuously, year after year. Our rovers have scratched the surface, not carved into it. Every assumption, how deep the ice lies, how pure it is, how easily it can be melted, carries uncertainty. A small miscalculation might mean slower production, more energy consumed, or equipment that simply cannot reach what it was designed to tap. And yet, the entire architecture of Starship's Mars missions leans on the assumption that this all will work. In the Starship vision, multiple cargo ships go first. They land, deploy reactors or solar arrays, assemble refineries, and quietly begin turning Martian air and ice into oceans of methane and oxygen. By the time the first humans arrive, their return fuel is waiting in frosty tanks, shimmering under the pale sky. That is the plan, but plans are stories we tell about the future. Reality writes its own chapters. If any major link in this chain fails, the ice is deeper than expected, the drilling equipment jams, the Sabatier reactors foul their catalysts, the power system underperforms, a dust storm cripples solar output for months, propellant production slows or stops. Maybe the tanks never quite fill, maybe they never begin to. For a robotic mission, such a failure is disappointing, but survivable. The spacecraft sits silently on the plains, another artifact of human ambition. Engineers study the data, adjust their assumptions, and prepare for the next attempt. For a crewed mission that relies on those tanks to leave, the stakes are very different. A short delay on Earth is an inconvenience. A shortfall in fuel on Mars is a sentence. Mars is not close enough for a rapid rescue. Launch windows open only every 26 months, when the orbits of Earth and Mars align favorably. Building a second, fully fueled ship and sending it in time to save a stranded crew would demand both extraordinary foresight and immense resources. Even then, everything would have to go right across both planets, on tight celestial deadlines. The uncomfortable truth is that, in its most ambitious form, the Starship Mars plan asks astronauts to stake their lives on a factory that has never been proven at scale, running on a power grid that has never existed, supplied by water wells that have never been drilled. This does not make the dream impossible. It makes it conditional on our ability to transform Mars from a silent landscape into a functioning industrial outpost, conditional on automation that borders on the miraculous, conditional on decades of engineering refinement, test missions, and incremental steps that slowly turn the unknown into the routine. One day, we may look back and see ISRU on Mars as a turning point, the moment when humans learn to live off another world, rather than simply visit it. But standing here, in the present, that future is still theoretical. A bridge drawn in fine lines across a gap we have not yet crossed. And for the first crews entrusted to walk that bridge, the question will not be abstract. It will be as simple and as profound as this. When they land on Mars, will the fuel to come home truly be waiting? History has a way of whispering warnings long before it raises its voice. In the story of Spaceflight, those whispers often sound like small concerns in engineering memos, quiet doubts in meeting rooms, or odd data points that do not quite fit. For a while, they are easy to overlook, until one day they are not. Long before anyone dreamed of landing a stainless steel tower on the surface of Mars, 3 astronauts climbed into a capsule on a Florida launch pad. It was January 1967, and the spacecraft was called Apollo 1. It never left the ground. Inside the command module, the atmosphere was pure oxygen at high pressure. Flammable materials lined the cabin. The hatch, designed to open inward, was difficult to remove quickly. Engineers knew these things. Some were uneasy. But the pressure to meet President Kennedy's promise to reach the moon before the decade ended was immense. Test after test had gone well enough. The risks, known but uncorrected, became part of the background. Then, during a routine ground test, a small electrical spark found its way into the oxygen-rich air. Fire in a spaceship is not like fire on Earth. It is instantaneous, absolute. Flames tore through the cabin in seconds. Gus Grissom, Ed White, and Roger Chaffee had no chance. The hatch would not open in time. Apollo 1 became a turning point. The program did not end. But it changed. Wiring was replaced. Materials were redesigned. Oxygen levels were reduced. The tragedy carved humility into the heart of Apollo. To reach the moon, NASA first had to learn to listen to its own discomfort. Yet history does not move in a straight line from ignorance to wisdom. It loops. It forgets. It drifts back toward convenience. 19 years later, in 1986, the Space Shuttle Challenger prepared for launch. The shuttle was meant to be a symbol of routine spaceflight, a reusable ship that could carry satellites, experiments, and even school teachers to orbit. It was, in many ways, a promise that space was no longer an extraordinary frontier, but something closer to infrastructure. The solid rocket boosters that powered the shuttle used rubber O-rings to seal their segments. Engineers at the contractor Morton Thiokol had seen something unsettling in earlier flights. The O-rings sometimes eroded under the intense heat and pressure. It did not always happen. When it did, the damage appeared manageable. After each successful mission, the concern seemed a little less urgent. This is what sociologist Diane Vaughan later called the normalization of deviance. A small flaw appears, but nothing catastrophic happens. The system survives. The risk, instead of triggering alarm, slowly becomes accepted as normal. Deviance, operating outside the original safety margins, quietly becomes the new standard. On the morning of the Challenger launch, Florida was unusually cold. Ice clung to the launch tower. The O-rings had never been tested at such low temperatures. Some engineers pleaded to delay the launch. They worried the seals would become stiff and fail to seal in time. But the schedule was tight. The program was under public and political pressure. Previous flights with damaged O-rings had still made it home. The risk was debated, then absorbed. The launch proceeded. 73 seconds after liftoff, a jet of flame escaped from a failed seal in the right booster. It cut into the external tank, igniting the fuel. In an instant, the illusion of routine was gone. Challenger broke apart, killing all 7 crew members. The lesson was not that spaceflight is too dangerous to attempt. It was something more subtle. That danger does not always arrive as a surprise. Often, it announces itself gently, through patterns of near misses and tolerated anomalies. It waits for us to treat it as ordinary. 17 years later, in 2003, Columbia returned from a mission that had seemed almost uneventful. During launch, a piece of foam from the external tank had broken off and struck the shuttle's wing. Foam loss had happened before. It was known. It had not caused disaster, at least not visibly. On earlier flights, footage showed pieces of insulation shedding from the tank. Each time, the shuttle survived. Engineers worried. Over time, the concern dulled. If foam came off and nothing catastrophic followed, perhaps it was not so critical after all. Once more, the normalization of deviance took root. On Columbia's final mission, When the foam impact was observed, some within NASA requested detailed imagery to assess the damage. Others argued it would not change the outcome. There was no known way to repair a damaged wing in orbit. The mission continued. The crew carried out their experiments, unaware of the true nature of the risk. As Columbia re-entered Earth's atmosphere, superheated plasma entered the hole in the wing. The shuttle disintegrated high above Texas. Again, everyone on board was lost. The pattern is haunting in its familiarity. Warnings emerge, anomalies appear. Rather than provoking drastic action, they slowly become part of the accepted reality. The extraordinary becomes ordinary. That is when hubris does its quiet work. This tendency was not limited to the United States. In the Soviet space program, secrecy added another layer to the story. Accidents did not simply fade into the background. They were often hidden entirely. In 1960, at the Baikonur Cosmodrome, a rocket on the pad exploded during fueling in what is now known as the Nedeline catastrophe. Hundreds of people died in a firestorm of burning fuel and debris, including senior officers and engineers. Official accounts minimized or obscured the scale of the disaster. Families were given incomplete explanations. For decades, the truth remained largely concealed. A few years later, cosmonaut Vladimir Komarov flew aboard Soyuz 1, a spacecraft with known flaws. Test reports had flagged multiple issues, from parachute concerns to navigation problems. Political pressure to keep pace with the American Apollo program pushed the launch forward. When Soyuz 1 re-entered, its parachute failed to deploy correctly. The capsule slammed into the Earth. Komarov died on impact. In an environment where failures were hidden, it became harder to learn from them. Errors could not be discussed openly. Patterns were harder to see. Without transparency, humility struggles to grow. Even Mars itself seems to teach a similar lesson. We imagine sending a large ship like Starship to land humans there, as though Mars were waiting patiently for us to arrive. But the planet has been quietly resisting our machines for decades. Throughout the history of robotic exploration, Mars has a reputation for being unforgiving. Orbiters that fail during insertion, landers that misjudge their altitude, parachutes that do not deploy correctly, communication links that cut off at the worst possible moment. Across all nations and agencies, more than half of all missions sent to Mars have ended in failure. Some were lost because of simple unit errors, like the Mars Climate Orbiter, which vanished because one team used metric units while another used imperial. Others succumbed to the thin, deceptive atmosphere that is too sparse for easy aerobraking, yet dense enough to generate dangerous heating and unpredictable winds. The lesson Mars offers is not that reaching it is impossible. It is that the margin between success and failure is narrow and shaped by details that often emerge only after we have tried and stumbled many times. When we talk about sending humans to Mars or landing a massive spacecraft like Starship on its surface, we are not deciding between safety and danger. There is no completely safe path. Risk is inherent. The real decision lies between acceptable risk and recklessness. Acceptable risk means more than courage. It means understanding failure rates, building redundancy, testing in conditions as close to reality as possible, and, perhaps most importantly, being willing to stop when anomalies appear, even if schedules slip and headlines sour. It means valuing one unexpected result over 100 successful simulations. Recklessness, by contrast, is not loud or obvious. It often looks like optimism. It sounds like, "We've seen this before and it was fine," or "We'll fix it later," or "The chances are low." It hides inside phrases like "good enough" and "within tolerance." It appears when we start treating nature as though it is obligated to behave according to our plans. None of this means we should not go. Exploration has always relied on people willing to face unknowns. But there is a difference between bravery and bravado. Bravery steps forward with clear eyes, informed by past mistakes. Bravado steps forward assuming that this time will be different simply because we want it to be. The harshest environments we have visited, low Earth orbit, the Moon, the fringes of Mars' atmosphere, have already shown us that they do not forgive assumptions. They reward only careful attention. As we consider Starship hurtling toward Mars, engines poised to relight in the thin air, tanks filled with fuel made on another world, it is tempting to see only the grandeur of the dream. But if history has a single consistent message for us, it may be this. The universe is more complex than our confidence. Every new mission is an encounter with what we do not yet know. Humility in exploration is not a weakness. It is a form of navigation. It allows us to revise our trajectory when new information appears, to treat each anomaly not as an inconvenience, but as a message. The disasters of Apollo 1, Challenger, Columbia, the hidden Soviet failures, and the many robotic losses at Mars are not just tragedies. They are signposts. They remind us that reaching another world safely is not just a matter of propulsion and engineering. It's a matter of listening, patiently, rigorously, to reality itself, especially when it contradicts our hopes. If Starship, or any vessel, is ever to land humans on Mars and bring them home, it will not be because we ignored these lessons. It will be because we learned slowly and painfully to treat every small warning as precious, every unknown as deserving of respect, and every success not as proof of invincibility, but as a temporary understanding waiting to be tested again. If our journey so far has lingered on risk, on fragility, and on the harsh arithmetic of physics and biology, there is another current flowing quietly beneath it. A different way of seeing the same equations. Where some see walls, others see scaffolding. Where some see impossibility, others see a to-do list. This is the world that SpaceX and its optimists inhabit. In their view, Starship is not a finished monument, but a rough sketch, a first draft in stainless steel. They would say that judging its ultimate safety and reliability now is a bit like looking at the Wright brothers' flyer and declaring that transoceanic flight can never be safe. Not because the concerns are wrong, but because the story is still on its first page. At the heart of this optimism lies a philosophy: fail fast, learn faster. Traditional spaceflight often moved like an ancient clock, carefully, slowly, each new mission following years of analysis, debate, and incremental adjustment. SpaceX has chosen another path, one closer to evolution than architecture. Build, test, break, learn, build again. We have already seen this with their rockets. Early Falcon 1 launches fell back to Earth. Falcon 9 boosters toppled, exploded, or missed their landing barges by heartbreaking margins. At the time, many observers believed reusable rockets were a fantasy, doomed by physics and cost. Yet, flight after flight, error after error, adjustments accumulated. Algorithms evolved. Hardware changed. What once looked impossible, the routine landing and reuse of orbital-class boosters, became almost mundane. From this perspective, the spectacular failures of early Starship prototypes are not signs of doom, but signs of progress. Each fireball is an experiment written in flame. Every shredded tank and shattered fin becomes a data point folded back into the next iteration. Optimists would argue that the only way to learn how a 120-meter rocket behaves in the real world is to fly it, break it, and try again. In their eyes, we are not looking at the final Mars ship. We are watching its ancestors trial and error their way towards something that does not yet exist. The same philosophy extends to rapid prototyping. Instead of building a single, perfect, expensive spacecraft in a clean room over a decade, SpaceX welds together multiple vehicles on an open plain in Texas. They accept imperfection at the beginning to accelerate refinement at the end. Those who embrace this approach often point to other technologies once declared impossible: supersonic flight, integrated circuits with billions of transistors, artificial satellites in constellations so dense they form moving patterns in the night sky. Each was met with doubt. Each required not a single breakthrough, but a long series of small, persistent improvements. To the optimist, Starship is another such frontier. They would say that we are poor at predicting the trajectory of technology once serious effort, funding, and iteration have begun. There is also the question of risk. Every concern about thin Martian air, searing reentry, engine relights, radiation, and fragile human bodies is, in part, a question about how much danger is acceptable. SpaceX's supporters often respond not with equations, but with history. They might remind us that the first humans to cross oceans in wooden ships did so knowing that many would not return. Early mountaineers accepted that some peaks would claim lives before they yielded roots. The first astronauts strapped themselves to rockets that had only just proven they could reach orbit. Exploration has always lived with a certain unease, a recognition that pushing into the unknown is never entirely safe. From this viewpoint, the goal is not to eliminate risk, but to understand it, reduce it, and choose it with open eyes. Optimists argue that going to Mars will never be as safe as boarding a commercial airliner. It may be more like joining a polar expedition in the early 20th century, dangerous, demanding, and undertaken by those who willingly accept the odds. They would say that there will always be people willing to face these risks if it means participating in the first steps of a multiplanetary civilization. Yet this perspective is not purely philosophical. It's also technical. Many of the systems that seem immature today may look very different by the time a crewed Mars mission is truly on the table. SpaceX and other groups are already working on technologies that, in the eyes of their supporters, could soften some of the sharpest edges. Heat shield tiles that crack and detach might be replaced or refined through hundreds of Earth re-entries long before they face the Martian atmosphere. Automated inspection techniques, real-time thermal sensing, and new materials could turn today's patchwork into tomorrow's robust shell. The delicate ballet of belly flop maneuvers and engine relights may be rehearsed again and again in near-Earth space, with uncrewed cargo flights serving as dress rehearsals. Each landing, whether flawless or fiery, feeding machine learning models, refining control software, and revealing obscure failure modes that no simulation could predict. Radiation, too, might be addressed in ways that are not fully mature yet, but are already being explored. Water walls doubling as shielding and life support reservoirs. Habitats partially wrapped in fuel, food, or even regolith brought from earlier missions and stored in orbital depots. Pharmaceuticals designed to mitigate radiation damage in cells. Perhaps even artificial gravity modules tested on long-duration Earth orbit missions before anyone commits to the voyage to Mars. The problem of weak muscles and brittle bones could likewise be softened by exercise systems far beyond the treadmills and resistance machines of the International Space Station. Centrifugal habitats creating partial gravity. Wearable robotics that add load to muscles during long periods of microgravity. Personalized counters to the subtle erosion of a body unmoored from Earth's pull. And on the surface of Mars, in situ resource utilization, making fuel, oxygen, and building materials from the local environment, might first be attempted with small robotic refineries. Failures there would be informative but not fatal. Over time, technology that once seemed speculative could become routine, its quirks and limitations catalogued and managed. From the optimist's vantage point, these are not distant dreams, but active lines of research. They would say that by the time humans are ready to step aboard a Mars-bound Starship, the vehicle, its engines, its software, and its life support systems may be descendants many generations removed from what we see tested today. Beneath this confidence is a deeper belief that we may be underestimating human ingenuity. Over and over, our species has encountered thresholds that seemed immovable, only to discover that the barrier was not a single wall, but many small steps waiting to be found. The first orbit, the first landing on the moon, the complex dance of satellites and probes now scattered across the solar system. Optimists suggest that our caution, while important, can sometimes cast the future in the shadow of the present. We see today's problems and assume they will scale linearly into tomorrow. But the history of engineering is filled with non-linear moments. Unexpected shortcuts, clever workarounds, quiet revolutions in materials, software and design. From this angle, skepticism and optimism are not enemies, but partners. SpaceX's defenders might argue that the harsh questions, the ones about safety, redundancy, medical risk, and unproven systems, are not reasons to abandon the dream, but reasons to refine it. Each criticism becomes a design requirement, each worry a test case. The most balanced path may lie somewhere between the poles of certainty and dismissal, between "it will never work" and "it cannot fail." To recognize that the dangers are real, profound, and non-negotiable, and also to admit that our ability to respond to those dangers is still unfolding. In the quiet of this reflection, it becomes possible to hold two truths at once. Starship, as it is today, may indeed be far from ready to safely land humans on Mars. The obstacles may be every bit as daunting as they seem. And yet, it is also possible that the story is not finished, that future iterations, future insights, and future generations of engineers and explorers might bend the arc of what is possible in ways we cannot yet fully imagine. Between caution and courage, between doubt and determination, the path to Mars, if it is ever walked by human feet, will likely be traced by both. We have wandered together through a landscape of uncertainties, a thin, stubborn atmosphere that refuses to behave like Earth's. Heat shields facing energies that turn metal into liquid. A vast stainless steel ship falling sideways toward a rust-red world, asking its engines to wake up perfectly in the final seconds every single time. Radiation slowly rewriting the chemistry of human cells. Muscles and bones dissolving into softness between worlds. A landing site that might hide its dangers beneath a veil of dust. And a refueling plan that depends on building a working factory on a planet we have never walked on. None of these challenges exist in isolation. Each one bends the others, like gravity curving the path of a passing spacecraft. A weaker crew is more vulnerable to radiation and injury. A risky landing amplifies the cost of a flawed map or a misbehaving engine. A failed propellant plant doesn't just end a mission. It turns Mars from destination into prison. The dream of a safe Starship landing on Mars is not a single question with a single answer. It is a web where every strand pulls on the rest. But this journey has not been about extinguishing a dream. It has been about holding it gently, turning it in the light, and noticing the fractures before they become catastrophes. Asking whether Starship could safely land humans on Mars is an act of care, not cynicism. When we question timelines, designs, and assumptions, we are not rooting for failure. We are quietly, stubbornly, insisting on survival. Throughout the history of exploration, every great leap has been built on layers of uncomfortable questions. Can the heat shield really hold? Did we test this valve enough times? What did we miss? The more we probe the weak points now, in simulations and in sleepless discussions, the less likely we are to learn our lessons in the thin air over Mars, when it is already too late to correct them. Skepticism, when paired with curiosity, becomes a kind of safety net stretched beneath ambition. If Starship, or something like it, eventually lands humans on Mars and brings them home again, that success will not erase the dangers we've explored. It will be built upon them. Every concern addressed, every failure analyzed, every nightmare scenario rehearsed in advance becomes part of the invisible armor around those future travelers, sleeping in their narrow bunks beneath an alien sky. Thank you for spending this time drifting through the science, the risks, and the possibilities. Your attention, especially in the quiet hours when the world is dim and the questions grow larger, is part of what keeps these conversations alive. If you found this voyage thought-provoking, you can gently support it by liking this video, subscribing to the channel, and leaving a comment. Let me know where you're listening from, what corner of Earth you're on, while we talk about another world. Reading those small coordinates of your lives turns this from a monologue into a constellation. For those who feel called to go a little further, there is also an optional YouTube membership. It's never expected, but always appreciated, and it helps us continue creating long, careful explorations like this one. As you settle into rest, you might imagine the future Starship not as a finished certainty, but as an incomplete sentence in the story of spaceflight. A possibility still being written, line by fragile line, in equations, welds, and whispered doubts. Between the dream and the danger lies the path forward, slow, deliberate, and honest. Somewhere, far beyond the clouds, Mars waits in its silent orbit, neither welcoming nor hostile, simply there. Our task is to decide how carefully we will arrive. And for tonight, it is enough just to drift with the question and let sleep carry you the rest of the way.